I'm Professor Rad, and this is Precalc video 3.8, graphing cosecant and secant. In our previous video, we talked about how to graph sine and cosine, and we were very careful in how we constructed those graphs following the unit circle. So we're going to be building on those concepts in graphing cosecant and secant, but we're just going to move a little bit more quickly. And then in our next video, we'll be graphing tangent and cotangent. So let's go ahead and get started. So remember, our x-axis is really our theta axis here. That's our argument. So our argument is going to be our angle. And then we're going to be graphing the ratios. So for cosecant, the ratio we're going to graph is 1 over y. And in secant, the ratio we're going to graph is 1 over x. So if I look at cosecant and I want to graph 1 over y, if I start here at this first point on the unit circle, when the angle is 0, the y value is 0, and we've just begun and run into an issue. So we've got 1 over 0, which is undefined. Great. Let's move on. So let's get to another point. Let's say if my angle is pi halves, here I have 1. Okay, this one I can do. 1 over 1 is going to give me 1. So when my angle is pi halves, cosecant, here's my pi halves, cosecant is going to be 1. Awesome. When I go to my angle of pi, I run into an issue again because I get 0. So let's just skip that one. When I go to 3 pi halves, I get to -1. So 1 over -1 is going to give me -1. So at 3 pi halves, my cosecant function is going to be -1. Great. So we're getting a few points. We can move clockwise as well. If we were to move clockwise, we would get at negative pi halves, we would get -1. And at -3 pi halves, we would get a +1. Okay. So here's our negative pi halves, we'd get -1. -3 pi halves, we get a +1. So now the question is, how do we connect these? What do we do? So we can't just connect them like we did with sine and cosine to get sort of a little wavy pattern happening, because we know we're going to run into issues at like 0 or 2 pi or pi, because the y values there are 0. So we're going to get something that's undefined. So do you remember our reciprocal function, f of x equals 1 over x? And if we think about what was happening there, when x was 0, here we had a value of 1 and -1. If I do 1 over 1, I get 1. And then we had sort of this drift happening. And at -1, we had -1, and then we had sort of this drift happening. So this is going to be relevant to when we go to graph secant and cosecant, because what we're really doing is from the interval from 0 radians to pi halves, it's going to be similar as when I go from my reciprocal function from 0 to 1, because my y values are going to go from being like 1 over 0 to being 1 over 1. So what that means is we're going to get an asymptote here. And from the asymptote until this point, we're going to look like 1 over x. Similar to it anyway. Then, as I go from pi halves to pi, I'm going to be moving from 1 over 1 to 1 over 0. So the same thing is going to happen, just going in the reverse. So I'll have an asymptote here at pi. I don't know why I made it so squiggly up there. And it's going to turn around and go up like that, because now we're turning around and we're going from 1 back to 1 over 0. So here's my 1 over 1. Now we're going back to 1 over 0. And you can do a similar kind of construction to get these negative pieces. They're going to look like negative u's, like upside down, things like that. So what happens for cosecant is we're going to be getting asymptotes whenever we have a pi a whole pi or a negative whole pi. And then we're going to be getting these fluctuating pieces that look like little u's. So this is quite a bit different from what we saw with our sine function, right? This is the reciprocal of the sine function. So the way that I like to think of it is like our sine function, which was these nice contained waves, has now like exploded outwards. So that little contained wave going like this has now exploded up and out to form this piece here. So that's our graph for cosecant. We can follow a similar method to graph secant, although this time we'll be looking at 1 over x. So x is going to be 0 at the pi halves or 3 pi halves. So secant is going to have its asymptotes not at the pi's, but at the pi halves. So we have 1 at pi halves, 3 pi halves, as well as at negative pi halves and negative 3 pi halves, and negative 5 pi halves and negative 7 pi halves, and so on. Then if I look at the x values, when my angle is 0, my x value is 1. So secant will be 1 over 1, which is 1. At pi, the x value is negative 1. So secant will be 1 over negative 1, which is negative 1. And then when we come full circle, we're the same as we were when we were at 0. We're going to be 1 over 1, which is 1. And if we go in the other direction, we'll be repeating ourselves here. And just like cosecant is an explosion of the sine function going out, secant is an explosion of the cosine function. So it's going to look very similar to here, just shifted a little bit. So we're going to have these pieces coming up, these pieces going down. And so on. So that's what we're going to get when we graph secant and cosecant. So just as we did, let me get out of the way. So if you wanted to pause the video and graph these functions, you can now. But just as we did in the last video, we looked at some properties of sine and cosine after we graphed them. Let's look at some properties of secant and cosecant that we can tell from their graphs. Alrighty, so let's start out by looking at properties of cosecant, and then we'll take a moment and we'll look at properties of secant afterwards. So right now, our focus will be on this top graph. So if I look at cosecant, for its domain, because it's a periodic function, it's going to extend forever to the right and forever to the left. But we have these issues where we have these asymptotes that are occurring on the pi's, basically, right? 1 pi, 2 pi, 3 pi, and so on. So for the domain, I'm going to say that our domain is going to be all theta, so that theta is not k pi, where k is an integer. In other words, we're allowed to have any value that we want for our argument, except for a whole number, positive or negative, multiple of pi. For the range, so the range of our sine and cosine function was trapped between -1 and 1. And cosecant is essentially the opposite of that, because it exploded the sine function up and out, or down and out. If we're looking at the bottom, we now have this like wasteland in between here where the function doesn't exist. So for our range, we're going to -infinity up until -1. And then we pick up again at 1 and go to +infinity. So the range of cosecant is going to go from -infinity up until -1. And we're going to include it because we have that point. And then we're going to union on going from 1 until +infinity. Again, including 1 because we have that point there. Remember that the period is how frequently the function repeats. So, or you can think of it as the interval where you get to see the whole scope of the function. So we've got this top u part here, and then this bottom u part here. And that's happening from 0 up until 2 pi. So from 0 to 2 pi, we get to see the whole scope of the function. So the period is going to be 2 pi. Now, like the sine function is odd because it's symmetric through the origin, the cosecant function is also going to be odd because it is also symmetric through the origin. So for example, if I have the point 3 pi halves negative 1, if I'm symmetric through the origin, I'll have the negative x, negative y. So negative 3 pi halves, positive 1. So that's a good little check that we can do. Or if I have, let's say, this point here, that's going to correspond to this point here if we reflect it through the origin. So we are symmetrical through the origin. So this means that cosecant of theta is an odd function, which means that if we have cosecant of negative theta, that's going to be the same thing as negative cosecant of theta. Okay, now our asymptotes we can also get from our domain. And now that we figured out where we were not allowed to have theta, that's where the asymptotes are going to happen. Just like when we had our rational functions and wherever the denominator would give us 0, it would be a problem spot for the domain and wound up being an asymptote, a vertical asymptote. So we have the same thing here. So our asymptotes are going to be of the form x equals or theta equals k pi, where k is an integer. And then lastly, this is kind of strange, for our x-intercepts, there are none. So because our range is everything below -1 or above 1, we never hit the x-axis. So cosecant has no x-intercepts. All right, so what I'm going to ask you to do here is to pause the video and see if you can fill in these same blanks, but this time using secant. So pause the video here, write out your own little your blanks, and use the graph of secant to fill it in. And then, of course, like usual, we'll go through it together. Alrighty, did you take the time to pause and identify those properties as practice? So let's go over them and use the graph of secant to find its properties. So I found that the domain of secant was going to be everywhere except for the odd k pi over 2. So we had issues at pi halves, 3 pi halves, and then we would continue to have issues at 5 pi halves, 7, and so on. Same thing with the negatives. Remember, we can't just say k pi over 2, because if k were an even value, like 4 pi over 2 would simplify to 2 pi. And at 2 pi, we're defined. We don't have an asymptote there. You could also write the domain here if you preferred. You could write that as theta does not equal, I'm short on space here, but I'll do 2k plus 1 pi over 2, where k is an integer. So that's another way that this domain is often expressed. So 2k plus 1 or 2k minus 1 is another way of writing an odd number. For the range, it's the same as for cosecant, right? Nobody's here in the middle. So we have from -infinity to -1 and from 1 to infinity. If I look at what's happening from, say, negative pi halves to 3 pi halves, we get the full scope of the function. We get the top u and the bottom u. So from minus pi halves to 3 pi halves is a total distance of 2 pi. So our period is 2 pi. Like cosine, secant is symmetric over the y-axis. So that means that it's going to be an even function. And so secant of negative theta is secant of theta. As with cosecant, our asymptotes are going to happen in the trouble spots from the domain. So we also could have represented this as k is equal to, or sorry, x is equal to 2k plus 1 pi over 2, where k is an odd integer. or k is an integer, I'm sorry. That could be another way to express it. But as I've mentioned in our sine and cosine video, for my classes, I'm going to be expecting the terminology that's in the blue. Okay, so these that I wrote here. And then just like cosecant, secant doesn't hit the x-axis ever, so it doesn't have any x-intercepts. So the last thing I want to talk about for these two functions is that just like with sine and cosine, if we take one of them and we shift it a little bit, we'll end up getting the other. So for example, if I take secant and I shift the whole thing to the right by pi halves, that will take this asymptote, put it on the y-axis, just like we have here. And it'll take the positive u and shift it so that it's in this section. This negative u will shift over here, and so on. So if I start out with secant, and then I shift it to the right, so I'm going to subtract pi halves, that will give me cosecant. And by the same token, if I start out with cosecant, and this time I shift it to the left by pi halves, that will give me secant. Right, so these are the graphs and some additional properties for secant and cosecant. That's going to conclude this video. We're wrapping it up. In the next video, we'll be repeating this whole process one more time for tangent and cotangent. So I hope you found this video helpful, and I hope you have a magnificent day, and I'll see you next time. Bye for now.